When linearly polarized light shines through sugar water, it produces a visual anomaly, a pattern of colored diagonal stripes. This video will use first principles to explain this phenomenon. We have three mysteries to solve. First, why does sugar rotate the polarization of light? Second, why does this twisting depend on the light's color, splitting white light into a rainbow? Third, why is the light beam visible from the side without polarizing filters? To solve these, we must look beyond Coulomb's law, which describes static force based on position. When a charge accelerates, we must add a correction term, which decays only as 1 over r. This radiating term dominates at a distance, and this is light. Influence takes time, propagating at the speed of light, c. The force felt by a distant particle depends on where the source charge was in the past. Therefore, a wiggling charge causes a second charge to wiggle after a delay. The radiating force depends on acceleration perpendicular to the line of sight. If you wiggle a charge, the resulting field is perpendicular to the line connecting the source and the observer. Propagation is strongest perpendicular to the wiggle. A single particle radiates in a donut shape. However, a wall of synchronized charges creates a directed beam. Constructive interference concentrates the energy forward, forming the familiar sine wave model of light traveling in a straight line. Visibility from the side is not light bouncing off a projectile. The incoming beam shakes a charge in the sugar water. That shaking charge becomes a new source of radiation, and we see the light emitted by the wiggling sugar water charges. Charges radiate perpendicular to their wiggle. If the polarization is parallel to your line of sight, the light is invisible. If the polarization is perpendicular, radiation is directed at your eye, and the beam is bright. As the polarization twists, the beam fades in and out. The polarization twist is uniform, but your viewing angle changes as you look down the tube. Where the wiggle aligns with your eye, it is dark. Where the angle shifts, light scatters towards you, creating the bright segments. The diagonal pattern is the result of the twist and the changing view. Light appears to slow down in a medium due to refraction. Sugar molecules are chiral, meaning they have a distinct handedness. This asymmetry means they interact differently with left-handed versus right-handed light influences. Linearly polarized light, which wiggles up and down, is mathematically equivalent to the sum of two oppositely rotating circular polarizations, a right circular and a left circular component. The direction of the linear wiggle depends on the relative phase of these components. Because sugar is chiral, it has two indices of refraction. It slows down left circular light at a different rate than right circular light. One component is delayed relative to the other as they travel down the tube, known as phase delay. When the left and right circular components recombine after the delay, their sum is still linear, but the direction has rotated by an angle theta. This explains why the polarization direction rotates. More sugar means more delay, which means more rotation. The interaction strength depends on frequency. Higher frequencies, like blue light, interact more often, leading to a stronger phase shift and a faster twist. Low frequencies, like red light, twist slower. This separates the colors down the tube, creating the rainbow effect. The mystery is solved. Visibility comes from secondary radiation from wiggling charges. The twist is due to chiral sugar molecules rotating the polarization. The colors are caused by high frequencies twisting faster, spreading the spectrum. All derived from the minimal assumption that accelerating charges radiate.